We're now going to look at another way of writing complex numbers known as Mod-Arg. So mod, or more correctly, modulus. You've actually been dealing with this for a long time because all that really is absolute value. So modulus is absolute value. So it's the length of, going back to our vector ideas, the vector OZ. So there's Z. If I was to join it up to the origin, I create a vector. Okay. So the length of that vector, or the magnitude of that vector, is what we call the modulus of the complex number. Now, if I drop in and get my vector, its horizontal and its vertical components, well, as far as our complex number goes, that becomes our real part and our imaginary part. So it means we can find it using what we saw in vectors. It's just the square root of x squared plus y squared. Or more interestingly, r squared equals x squared plus y squared, which we have seen quite a bit now. Now the symbol we use for modulus is the absolute value symbols, because as I say, essentially modulus is absolute value. Absolute value of z, or modulus of z, is the square root of x squared plus y squared, so the distance formula. Argument, and we've seen this idea before as well, but the argument is the angle that vector will make with the positive x-axis. Again, that's what we saw with direction of a vector. So it's the same thing. So theta we tend to use for the argument of z, or just simply arg, and then whatever the complex number is. And we work it out the same as we always do, inverse tan of y over x. We just got to be very careful with this so we know which quadrant we're in, because remember, when you go inverse tan, it has a range of minus pi on 2 to pi on 2. But of course it is possible to have arguments outside that. So we have to be very clear which quadrants we're in to work out the argument. Argument, what's known as the principal argument, is always in between minus pi and pi. You'll notice there is no equal sign on the minus pi side, because you can't have two arguments for the one number. So when we are on that position where it would be pi or minus pi, it's always the pi that we go with, not the minus pi. Let's do it to this one here, 4 minus 4i. So we work out our modulus, turns out to be 4 root 2. The argument, now notice how I've written it. I've made it very clear where the negative sign is, because that's going to help me identify the quadrant. In fact, it's even useful to draw a diagram. It is the inverse tan of minus 1. But as I say, the calculator, in this case, will be okay, because you'll notice we're in the fourth quadrant, and the calculator would have given me that answer. So that's fine. But imagine if it had been 4 over minus 4. I mean, the calculator is still going to give me the same answer. But in that case, we wouldn't be in the fourth quadrant. So that's why a quick little diagram can help, all right, locate exactly where you are. So minus pi on 4 is my argument. So every complex number, just like every vector, can be written in terms of its modulus and its argument. So z equals x plus iy, when we've got it written in that component form of vectors, could now be rewritten this way. Using that right angled triangle, I could work out that x is equal to r cos theta. Just a little bit of trig will work that out for us. And y would be r sine theta. Well, there's a common factor of r, so we can pull that out. It'll be r cos theta plus I sine theta. Now, there is an abbreviation for this. Be wary of using it in certain situations. And that's what's called the cis notation. The reason I say be wary of using it, because if you're using cis theta at the same time as you're doing trig, it's so easy to mistake the cis theta for a cos theta or the cos theta for a cis theta. So just watch out for that. So z is r cos theta plus I sine theta. As I say, it can be abbreviated as r cis theta, and r is the modulus, theta is the argument. Which means our number we could rewrite like so. 4 root 2 cis minus pi on 4. These coordinates we're using are another form of coordinates on the number plane that's used in other areas as well, not just complex numbers. It's what's known as polar coordinates. Okay, root 3 plus I, what would that be? And you'll see this combination of numbers happen a lot. root 3 and 1, things like that, because they're our exact triangles, sides than that. So we know we'll get an exact value. Modulus is 2. The argument for this one, inverse tan of 1 on root 3, there's that exact ratio we're familiar with. Pi on 6, because we're in the first quadrant there, so it would be that acute angle of pi on 6. That means we could rewrite it as 2 cis pi on 6. If I want to go back the other way, well, they've given me 6 cis pi on 6, but to convert it, it's much easier to think of it as the actual cos theta plus I sine theta. Pi on 6, cos of pi on 6, what's that? Root 3 on 2? Yeah. So we sub in, we've got root 3 on 2, and sine of pi on 6 is a half. Expand out, there's our answer, 3 root 3 plus 3i. So how do we play with things when they're in Mod-Arg form? How do we add them, subtract them, things like that? So some patterns which will always be true. If you want to multiply two complex numbers together, again, it does not matter the order you do it in, you could multiply them first, then find the modulus, or you could find each moduli and then multiply them together. With the arguments though, you add. So this is very much like logarithms with the arguments. You remember when you multiply, you add? Same sort of idea. So if I want to find the argument of Z1, Z2, I would add the two arguments together. Multiplication rotates Z1 by Z2. Because what we're basically saying is the angle of Z1, we're adding the angle of Z2. So you get this rotation. Okay, I'm going to prove these relationships. So Z1 I'm going to call R1 cis theta 1, Z2 R2 cis theta 2. So if I multiply them together, this is what I'm multiplying. Well, the R1 times the R2 is easy enough. Pull that out, but then expand our binomial and we see a lovely familiar pattern. Look at the real part. Cos, cos, sine, sine. If it's not the sine, it's not the sine. And look at the imaginary part. Sine, cos, cos, sine. If it's the sine, it's the sine. Which means we have got cos of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So there we have it. The modulus turned out to be R1, R2, which is modulus of Z1 times the modulus of Z2. And the argument turned out to be theta 1 plus theta 2, which is the argument of Z1 plus the argument of Z2. Now you can expand that idea, of course. It doesn't matter how many you've got, this relationship's always going to be true. So if I've got, well, n complex numbers multiplied together, then I could work out the modulus by just multiplying the modulus of each of those n complex numbers. When it comes to the argument, I would be adding all of those arguments together. Okay, division. Similar thing happens. I can find the modulus first, or find the moduli of each and then do the division. But when it comes to the argument, we'll subtract. We subtract the arguments. Now, I didn't bother with a proof for that one, but it's very similar to the other one. But it will then follow, if I had something like this, the modulus of Z1, Z2 on Z3, Z4, then I could break up the individual moduli. But with the arguments, all I have to really know is that if it's on the top of the fraction, it's going to be plus that argument. If it's on the bottom of the fraction, it's going to be minus that argument. So I get arg Z1 plus arg Z2 minus arg Z3 minus arg Z4. Raising a complex number to the power of n, well, we just said with the multiplication, I could get each individual moduli multiplied together. Well, in this case, it's to the power of n. So therefore, I've got n of them multiplied together. That would be the modulus of z, all to the power of n. But when it comes to the arguments, because I'm adding each of those, I'll end up with n lots of the argument. So if I want to find the modulus and the argument of this particular complex number, I could do it a really long way. I could go and actually calculate what this is. And sure, then go and work out the modulus and argument of that. That would be the long way of doing it, when it's going to be probably quicker to find each of the individual moduli and then work out what that number is. Oh, look at that, 13 goes into 26. Wasn't that lucky? We end up with root 10. Heck of a lot quicker than actually calculating the number out, then going and finding it. The arguments, well, in this one I'm going to have to do an approximation or play with inverse trig here. because we don't have exact values for a fifth or 2/3. I'm going to go back to degrees. It is unusual to use degrees for this. Normally you'd always be using radians, but just for the sake of approximation, I've gone back to degrees for it. And we'd end up with minus 175/48. Notice the middle one there. I didn't write it as a half, I wrote it as -1 on -2, just to remind myself, they're both negatives, therefore I'm in quadrant 3. So what happens when we shift the reference point? Now, we're not always going to be connected to the origin, just like vectors. You can move a vector around. We know this circle, we've moved the center from the origin to the point 1, 2. Okay. We could do exactly the same for anything, because the Argand diagram is essentially the number plane. So all those ideas we've seen in curve sketching, we can use in the Argand diagram. So there's a point x plus iy, so some random complex number. And sure, modulus of z would be the distance from z to the origin. The argument of z would be the angle it makes with the x-axis. But let's say there's this other complex number over there, and we're asked to find what's the modulus of z minus w. We just got to think about what is it saying. Modulus just means distance. Now, modulus of z was distance from z to the origin. But in reality, what you're saying is it's the modulus of z minus 0. Head minus tail, exactly the same as vectors. So when I see something like this, z minus w, what does it mean? It means the length of the vector that's joining z to w. That's what we're trying to find. And the argument would be the angle it makes with the horizontal at the tail. So whatever alpha is for this one. Okay. 1,